Okay, good afternoon, everybody. I'm Alex. I'm from the Leaders Award team. We've also got Jess here from the Leaders Award team as well. Welcome to this Leaders Award Home Learning Online interview featuring Ford Automotive engineer Oliver Joris. Just before we get to Oliver, I'll just run through what's kind of going to happen in the next hour. I should tell you that because there are lots of people watching this event, everyone's muted except for Oliver and I for the whole event, just so there's no kind of interruptions, distractions, or real loud feedback. The first part of the event will be Oliver's presentation, which shouldn't last more than 15 minutes or so. So please feel free to type in your questions at any point during the session so that when we get to the Q&A section after Oliver's presentation, we can get straight into answering as many of your questions as possible. Participants should use the Q&A facility that's at the bottom of your screen. It should be kind of next to the chat facility as well to type in your questions there for Oliver. This will be similar to those who are watching on Facebook. We're streaming this live on Facebook as well. Please can you type your questions into the comment section there. I will then relay the questions to Oliver for him to then answer. Just before we get to Oliver, I'm just going to explain, however, a little bit about the Leaders Award. If you were an engineer, what would you do competition, and kind of tell you all about it. So what is the Leaders Award if you're an engineer competition? If you're an engineer, what would you do competition? Its main aim is to inspire young people ages 3 to 19 to look at the world around them and design solutions to problems, which is what engineers do every day. We provide opportunities for you to meet and interview engineering professionals online, just like we're doing today, to inspire you to think of ideas and start designing some inventions from that. To help you with this, we have also lots of available resources on our website. So after our interview today, make sure you register for those as well. Our suggestion is that you make this a weekly challenge, interviewing engineering professionals online every week, looking for different problems in the world you'd like to solve. Just before you then head back to school, you're going to choose which idea you think is the best, take this into school where you can then send in those from your school to our engineering professionals to read. This session today is booked till 11:30, so without further ado, I'll now pass over to Oliver Joris, who I mentioned before is an automotive engineer for Ford Motor Company. Hi, Oliver. Can you hear me?
Good morning. I can hear you. Thank you very much.
Fantastic. I'll just stop sharing my screen, and then you should be able to share yours as well.
Okay. Let's share this screen. Right. Can everybody
That's perfect.
see? Is that okay? Right. Good morning, everyone. My name is Oliver Joris. Thank you for the introduction. I'm an automotive engineer at Ford Motor Company, which essentially means that I work on cars. Automotive is a fancy word for car. Engineer is a word for a person who designs, builds, or maintains engines, machines, or structures. So an engine tends to be, I suppose, sort of like a machine, but it tends to convert energy types. And a structure would be things like bridges or buildings, for example. So in my talk, I'm going to talk a little bit about why I became an engineer, what the company that I work for, Ford, does, what engineers do where I work, and what I do as an engineer. So here's a little bit about me. I'm a little bit crazy about cars and motorbikes. So in the top left, that's me with my father and my brother at a classic car show that we went to. In the top right, that's me with some friends and colleagues from Ford. That was a weekend driving around Wales, very much pre-COVID-19. And then in the bottom right, that's one of my bikes. That's me at Brands Hatch going around a track. In the middle is what the Mini's looking like at the moment. I'm currently running a project at home, and the attempt is to create an electrified classic Mini. So I'm going to try and make my classic Mini electric for the environment and as a challenge project to myself. And then the bottom left, another one of my hobbies is what some people call adventure riding. So that's me with a couple of friends, and that's us in Morocco. We were riding around Morocco, and then we rode back up to the UK for one of my holidays. So that gives you a little bit of an idea about what I do in my spare time. But really, that probably gives you an idea of why I became an engineer. So a little bit about Ford. In 1896, which is a very, very, very long time ago, a man called Henry Ford decided he enjoyed playing with cars, well, playing with machinery like I do. And so he decided to start experimenting and made this quadricycle. So quadricycle is a fancy word for a bicycle with four wheels, but he's added a little motor at the back there. His idea then turned into the Ford Model T, of which they produced loads and loads and loads. This was one of the most popular cars of the time, and it actually led to the adoption of vehicles as we know it today. So on the right, I've shown a couple of photos of a few of the cars that we're working on to give you an idea of the range of what Ford builds. So at the top there is a Fiesta ST, which I suppose is the perfect sort of compromise of fun, practicality, and something that's affordable. In the middle there is something that's definitely not affordable, but is the extent of what Ford's capable of at the very high end. So they make very fast cars. This is one of our GT cars that won a load of races at Le Mans, which is a big event. And then at the bottom there is one of our very practical vehicles, which is the 2-ton Transit. So a big part of what Ford does is it makes vans and trucks for companies so that they can ship things and people around. So here's a slightly bigger product lineup. I'm not sure. Product is just a word that we use for our cars and vehicles. And you might have seen some of these on the road. Some of you might have parents that own some of these, and then some of them probably not. So we go from the Fiesta all the way up to the Cargo in the bottom right. So lots of different shapes and sizes for people's different needs around the world. So I did just say around the world. Ford is a global company. I work at Ford alongside about 200,000 other people who keep Ford running on a daily basis all around the world. And we have design centers and factories, which are buildings in which people build things all around the world so that we can cater vehicles to people in all markets. Now, to do that, we have these assembly plants. Assembly is a fancy word for putting things together. So you might say you assemble Lego. In this case, it's very much like that, except we're assembling bits onto cars. So this is a Fiesta assembly plant where all these Fiestas are carried around on these yellow cranes, and they go through a bit like a roller coaster, but very slowly. They go all the way through the plant, and every sort of 30 seconds, they'll stop, and then someone will hop in and they'll put in, say, the seats or the steering wheel or the headlights, and then it goes through the end, and then at the end, somebody starts the car and drives it out into the car park. Now, as well as factories, we have technical centers. So I work at a technical center, which I'll talk you through in a moment. And at these technical centers, what we try to do is we try to imagine what people would want in 6 years' time, because that's how long it can take to develop one of these vehicles. And we try to draw and design the sort of car that would meet our needs in 6 years' time. So that's what we do in these centers. And then throughout the 6 years, we build up these vehicles and we test them so that then 6 years later we can sell them and hopefully sell a product that everybody enjoys. So I work at a technical center called the Dunton Technical Center, which is on that map there just to the right of London, to give you a vague idea of where we are. In the picture on the left, you might be able to make out a load of buildings and a load of car parks. There are, I think, about 3,000 of us working at Dunton at the moment. Well, not at this moment, we're all working from home. but when we're all back on site. And so there's lots of car park spaces, not just for our prototype vehicles that we drive around, but also for us to get in. On the same image, you can see the 2 tracks that we have on site. So the top track there is our high-speed track. That's a big loop. I think it's 1.7 miles with 2 banked corners, which means the corners are on a side slightly so that when you drive around them at 70 miles an hour, you can go around very quickly and stay on the road. And then at the bottom there is our other track, or our multi-surfaces track, which is a track that has lots of different types of road, like cobbled roads, stony roads, that sort of stuff. And we drive along them and make sure that the noises are acceptable as we're driving along those roads. So at the Dunton Centre, we design and build engines. An engine is the block that sits under the hood at the front of the car, which moves the car forward. So what we do is we take petrol, which you may have seen your parents pour into the back of a car. That petrol gets burnt, which causes a mini explosion, and we use that mini explosion to move the car forward. So everything that allows a car to move, we design here. So that involves an engine, a gearbox, and in this case, you can see the drive shaft as well. But don't worry about that. So here's a short video of what we do on our site. Here you can see the car park filling up in the morning for all those people coming in. This is our front entrance. This is our statue of Henry Ford, stood watching over us as we work. This is the Costa coffee bar on site, which is probably the most used facility on site. And here's a little video of our high-speed test track. So there are those banked corners, and this allows us to do a continuous 40, 50 miles an hour and 70 in the straights. And this is one of our special road surface tracks. So you can see there's little humps and bumps as well. So we can test things like starting and driving uphill, downhill, and handbrake turns. We also have a design center where they draw and then 3D print some of the cars and also mill them out of clay. So the word CAD here is computer aided design. So he's using a computer to help him design, in this case, a wheel. Something as simple, some might say, as the color of a car takes 3 years in order to make sure that we get the right sort of colors. And here is one of the colors being tested. The design center like to use clay models because it's something they can work with very quickly. And then we start testing engines in a room. So here's an engine in a test chamber, which I'll explain a bit more about later. And then our vehicles, again, I'll talk through this a bit later, get tested hot and cold to make sure they work the way they should do. We also pride ourselves on community involvement at Ford. So here's some of the events. We do the Lego Challenge and some of the green power stuff, which some of you might have heard of. And then here's a fancy flyover shot, I think. There we go. So obviously, if you have any questions about that, feel free to ask me afterwards. So my job is to check that the engines in our cars work as they're supposed to all over the world. What you'll find is that if you sell cars all over the world and use them all over the world, they can get very, very cold and very, very hot as well. So we have to make sure they work in the Arctic at -30, but we also have to make sure they work in the deserts at +40. Engines can get too hot and they can get too cold. If they get too hot, they can damage themselves. And if they get too cold, generally they won't start, which could leave some of our customers stranded. I have a laptop that plugs into the computer on the car. So every car has a little computer built in that controls the engine and my laptop can speak to that computer. So our two computers talk to each other, and they tell each other all sorts of things, like, for example, the temperature. So the engine can tell me whether it's too hot or too cold while it's driving around. Here's one of our hot testing days. Recently, we've had some really lovely hot weather in the UK, but as happened, and as always happens, this week things have got a little bit colder. Now, for our tests, we need to run our tests at a very specific temperature. So if I need to know that it's going to work in the desert, I need to be able to run some tests at desert temperature whenever I need it. So this room here, I can set to that temperature. This room can go to 40 degrees hot, and you can just about see the lights at the top that can do what we refer to as sun loading. So you can say, okay, I want a really sunny day in the desert. And then you can drive that car. See, the wheels are on rolls. So the car actually stays in the same position, but the wheels move. So it's like we're driving along the road, but we're going on at 40 degrees. And so I can test the car in desert conditions at our site at Dunton in the UK every day of the year if I would like to. We can also do that with cold. So we have these big fridges, and we can put the cars in the fridges and go down to minus 30 degrees. And then we can start them up, and it would be like we were starting a car in the Arctic at minus 30 degrees. Once we've collected all of this data, it's our job as an engineer to make sure that the data is used properly, but then it's also our job to make sure that the engine does what we want it to do in the real world. So as part of my job, I get to drive around the world and test these vehicles in these conditions. So this is me testing the Focus that's going to be launched in China at minus 30. This is me in the Arctic Circle in Finland. And just to give you an idea of how cold minus 30 is, here's a video of my friend Mark. He's about to throw a cup of boiling water. At minus 30 degrees, a cup of boiling water thrown into the air instantly turns into snow. And here's me up Großglockner in Austria at 2,430 meters high. So we also have to test our cars at altitude. And to give you an idea of how high that is, the Big Ben, which you might have seen, is just under 100 meters. And this is at 25 Big Bens in altitude, or height. Altitude is just a fancy word for how high we are. And then here's me. We also do some trips in the UK. Here's me at the Land's End. Here's me at Land's End to do our work at sea level and what we would consider normal temperatures in the UK. So the takeaway messages, i.e. the things that I'd like you to remember if somebody said, what was that talk about you just listened to? Was that I'm an engineer because I like playing with the engines in cars and motorcycles. The cars that we use the engines that we design power the cars to move forward. And we do a lot of work to make sure that those engines are as powerful as our customers want, but also run very efficiently, i.e. they give you as much power as possible for as little bit of fuel as you put in as possible. Our cars are designed and programmed in these design centers, like the center that I work in, and we can, in our design centers, put our cars into all sorts of environments around the world, hot, cold, high altitude or low. And cars are tested all over the world to make sure that they work. So just as an outro, here's my team waving away from the top of the mountain. All righty. Thank you very much.
Thank you so much for that, Oliver. That was a fantastic presentation. Usually videos don't actually work on Zoom, but yours seem to work fine, which well, it worked for me anyway. I hope it worked for everyone else. I'm sure it did. I'll just make sure your screen stops, so you're on the screen there. And then there's some questions already come flooded in on the Q&A section, so I'll just open that up and ask you some questions off there. Just to remind everyone, if you want to type in your questions on there, or if you want to type in the chat, then I can then relay them to Oliver. Also on Facebook, if you want to comment in the comment section and ask your questions there as well. The first one, just to do with when you said about going to Brands Hatch, it says, how fast was your time at Brands Hatch? That's from Bryony.
That's a very good question. That was my first go, so I did not time because we weren't allowed to. They're slightly worried that if you start timing yourself, you might start taking unnecessary risks. So I'd like to say it was obviously under a minute, but it definitely wasn't, I'm sure.
So we've got one from Lakindu. So what is your favourite car, Oliver?
Oh, that's a good question. It's a very difficult question to answer because it depends on what I'm using the car for. So I'm very fortunate to have a few cars myself. And I'd like to say that my classic Mini is probably my favorite car.
So I think you're under pressure to say Ford, aren't you? I think then.
I probably should. So I thought I'd go with one that wasn't in production.
Yes. So what made you want to become a Ford engineer? That's from Katie.
That's a good question. Ford makes cars, which is obviously one of the reasons that I wanted to work for them. But more than that, they're also there's also a great community feel to the company. And when I applied to the company, that was something that was important to me. So a lot of the community events that they do, a lot of events like this that they support me doing, and I'm very pleased that I'm able to do with your help is exactly the sort of reason that I joined the company. Even through the times, but also through my time there, I think they've always done the right thing, and that's important for me to be working for a company that I want to be working for.
So we've got another question from Katie. So when and where did you start as an engineer?
Well, it's a good question. Sort of depends on, I suppose I'd like to think that engineering is a bit of a mindset. So I'd like to think that it probably started from a very young age playing with Lego. Officially, I became an engineer the moment that I received my engineering degree, which was, 2004, I think. But then I did a PhD. So I went into research for 3 years, and then I started at Ford about 6 years ago. So I started working as an engineer 6 years ago. I was technically qualified as an engineer more like 10 years ago, but I reckon I sort of had that engineering mentality from a very young age.
So I think you kind of touched on this in your presentations. So Rohan's asking, what exactly kind of do you do in your job? So what are kind of the specifics, I think, in your job?
Okay, thanks, Rohan. Day to day, at the moment, I'm an onboard diagnostics engineer. So onboard diagnostics are tests that the computer on your engine run all the time. So every time you turn your car on, it runs thousands of tests. And I make sure that those tests do what they're supposed to. So even though I'm working from home at the moment, I have 2 cars on the drive, 2 prototype vehicles. And I plug my laptop in, and I pull all sorts of wires out or give it the wrong sort of code. And then I make sure that it can tell me what's gone wrong. And then when I fix it, that it tells me that it's fixed. That's what I do on a day-to-day basis.
So we've got one from Lakindu. So, this is a really interesting one, which you were talking about the cars going into different temperatures. So she's asked, does a person travel in the car when it's being tested different temperatures?
Yes, they do. We do have robots. So we can set up robots to drive certain conditions. But they're actually, for the amount of tests we need to do, they take a while to set up. So it's easier to have us in them. So yes, I have spent very cold mornings in a car. You also have to have the window open, which is one of the safety regulations. So yes, I've often sat in a car with minus 30, 70 mile an hour wind blasting across in my woolly hat, wishing that I was in Costa having a coffee. It's a good question.
So Greg's asking, what size and type of engine does a Mustang have?
Oh, well, the Mustang goes up to a 5 litre, which is big, which is very big. But then it's a very powerful car, and it's a muscle car, so it needs a big engine.
So Lakindu's asking another question. If you couldn't work, or if you didn't work at Ford, where would you want to work?
Ooh, that's a good question. Essentially, as an engineer, I like playing with big machinery. So one of the things that's fun about Ford is that it has things like the facilities that I mentioned that do hot and cold, high altitude, low altitude, the tracks. I get to travel. Some of the places I've worked at before as a scientist are big accelerators. They're big toys, as far as I'm concerned, big pizza kit that cost millions and millions and millions of dollars. And if I wasn't working there, I wouldn't be able to use that sort of, I wouldn't be able to work with a toy that big, if you see what I mean. So anywhere really that had the sort of technology that I couldn't play with at home.
So we've got one from Brian. Are you developing any cars that run on hydrogen?
Oh, that's a good question. Ford specifically, I think, has chosen to push electric rather than hydrogen at the moment. And a lot of that is due to the progress in battery technology that means that actually the segment in which hydrogen fuel cars makes sense is becoming smaller. So there's definitely something to be said for hydrogen in the commercial space, i.e., when I say commercial, I mean businesses. There's something to be said for bigger trucks because you'd have to have a very big battery to lift all of that weight. On passenger vehicles, it doesn't really make sense. Electric vehicles have come so far that running a battery makes more sense. So yes, it's being looked at, but really probably only for commercial vehicle applications. And even then, at the moment, definitely going for the hybrid strategy of running an internal combustion engine combined with electric rather than going hydrogen at the moment.
So we've got a question from Rohan. What different jobs are there? So I'm guessing that means at Ford, how many different kind of jobs are there at Ford?
That's a good question. Even when I completed my engineering degree, I wasn't sure what an engineer actually did on a day-to-day job. I was very fortunate to join the graduate scheme. So I had 3 8-month placements, and then I've had 2 jobs since then. So in the 6 years, I've actually done 5 different jobs. And that's ranged, I suppose the easiest way to think about it is to think of the timeline of the development of a vehicle. So you start very early stages. You think about what it is that a customer might want in 6 years' time. A lot of that is defined by the government in terms of emissions levels, in terms of safety standards. But some of that is what customers want, what they expect from a Ford vehicle, for example. So we would refer to that as our DNA. So very early stages engineers will look into what parts are available. A lot of cars are, we design and assemble systems really, but a lot of the parts arrive from suppliers. So things like oil pumps, seat belts, that sort of stuff. We need to know what's available in the sort of volumes that we need them, i.e. the sort of number that we need them. And then put that together with the requirements. All the way through, we then have engineers that start fitting those bits and testing them. And then all the way at the end, you get to my end where we make sure that all of it works together as it should do before it's sold to our customers. And then even then, once it's sold to customers, we have people who look at feedback from customers to check that what we intended to do 6 years before then, we're actually doing, and then learn those lessons for the products that come 6 years from now.
So we've got a question from Katie. It says, what is your favourite car? I think we've had that one before, where we talked about the Mini, wasn't it? What's your favourite car at Ford, did you say?
That's a good question. I should definitely answer that question. Again, I know this is not the answer you're looking for because you'd rather I gave you one, but I've driven the Mustang, and that was an incredible feeling. To feel that power was really fun. I've also driven the RS. The handling of that was unbelievable. So in that sense, I'd probably say the RS was the performance car that's my favorite. In terms of practicality, I've also had the pleasure of driving the 2-ton Transit. In fact, we were doing some cold weather testing in Finland And so we did some evasive maneuver driving, and it was incredible to see how that thing handled on ice, and is incredibly practical. So it depends on the task at hand and the journey at hand. All round best car, if I had to pick one, would probably be the Focus RS. I'd say that would be my favorite.
We've got a question from Jed. So why don't cars fly at the moment?
That's a good question. One of the issues with flight is pilots. Issue's the wrong word, but pilots are very highly trained, and they're incredibly competent, and they work shifts, they work together, they work and they're heavily scrutinized. If you start giving planes to everybody, chances are you're going to have quite a few accidents. So I think a key part to getting flying vehicles working is autonomous control. Autonomous control is something that Ford's pushing at, like a lot of companies. They're investing a lot of money into it and making some good progress. I think making a flying car isn't the difficult part. It's making a flying car that can be used by people. And so once we've sorted out how to do autonomy on the road in 2 dimensions, I'm sure the next step will be figuring out how to do it in 3 dimensions, at which point we can all expect to have autonomous flying cars.
So Rohan's asking, what are the differences between different engines?
Good question. Good question. Again, so a bit like you would scale the size of a car for the need. For example, you might, as a small family, you might have a Fiesta. As a big family, you might have a Galaxy, for example. Those bigger cars need more power. So you could argue that both of them only really need to be able to go up to 70 miles an hour. And people would like it to accelerate relatively quickly, but really people are pushing for efficiency. So you would scale an engine based on the power that's required to move a car at the speed that people expect it to move. And that will differ depending on the weight of the car. So, for example, our smaller cars use our 1 litre engine, which is a 3-cylinder engine that's very powerful for its size. But if we were going up to a bigger car, we would put in our 1.5 litre engine that's more powerful and able to move a bigger car at the same speed. So size of engine is important. But where to explain what differences we put in engines, we have to explain a little bit about how an engine works. So I'll try and keep this very brief. But essentially, an engine combines air and fuel and explodes or ignites that air and fuel to make an explosion. The more power that you want, the more air and fuel you need to have, which is why going from a 1 litre engine to a 1.5 litre engine. And when I say litre, I'm talking about the size of the cylinder, which is where the air and the fuel mix. If you have a bigger volume, you can produce more power. Another way of doing this, you may have heard of turbos, is that you can use the same volume, but you can use a higher pressure. So a turbo pushes more air into the same space. If you've got more air, you can use more fuel. And if you have more fuel and more air, you have more power. So one of the things we've been doing, the reasons we've been able to make such small, powerful engines is that we've been boosting them, as the term. We put big turbos on and put the air in at higher pressure with more fuel. Sorry, that was a bit technical, but that's
No, I think that answered the question really, really, really well.
Okay.
So Greg's asking, what subjects are needed to become an engineer?
That's a good question. It was a long time ago, believe it or not, when I applied. So things are a little bit different now. But the things that have been most useful to me are maths and physics. Of course, it depends on what kind of engineer you want to be. My wife's a chemical engineer, so for her, maths and chemistry made more sense. But essentially, the sciences and maths. I would also add to that that at the moment, electrical is a big thing. It's everywhere and anywhere, and coding is a big thing. So if I were hiring an engineer, or if I were bringing an engineer to train them up, I would want them to be familiar with physics, maths, and coding. A lot of what we do now is coding.
So Jed's asking, what is the biggest engine you have seen?
The biggest engine I've seen is probably the, where was I? I was at the Museum of Power just off Chelmsford. Oh, I wouldn't want to say how big. The engine was probably the size of, it was the size of a double-decker bus. And it was very old, steam driven, and used to pump water. So it was, I think it was, yes, that's right, it was water pumping. That was a huge engine, and really fun to see that in real life.
Katie's asking, what did you have to learn in school? So I think it's similar to what Greg was asking about the subject. So what did you kind of have to learn in school to be an engineer?
Yeah, I think one of the key things I like telling people when they're applying for engineering is that they tend to be quite clear about which subjects you need. So you tend to want maths and physics, maybe another science, and as I said, maybe some coding. One of the other things that's important is the extracurricular things that you do. So one of the things my university was pleased at when I applied was things like the team sports that I played, things like music. I know it sounds silly, but the arts are actually a great way of visualizing things, and so I'd say for me it was a combination of team sports, and being able to work in a team is incredibly important for engineering. We do have the odd example of an individual coming up with some eureka moment, but more often than not, these eureka moments come about through teams working together on a global scale, hundreds, if not thousands, of engineers chipping away at a problem and refining a product to make something that really makes a difference. So I'd say, check what subjects are required from the university or the course that you're looking to apply to, but also try and work on the extracurricular bits and pieces that would increase your ability to work in a team, to listen to people, to really refine ideas, and follow some blogs, follow some YouTube series on engineering or manufacturing, maybe even some books, and it's little things like that that show that whoever it is that's interviewing you knows that you're really interested in the subject, and not just looking to do it for some other reason.
Just coming away from engineering slightly, Oliver, is there anything you like to do kind of outside of engineering to kind of de-stress or anything like that?
Well, I suppose music's an example. So I like to learn all the time. So very fortunate that Ford runs a extracurricular activity center as well. So through Ford, I have my guitar lessons. So I do guitar. I sing. I enjoy things like cooking, I suppose. But I was just trying to rack through a hobby that wasn't engineering related. A lot of what I like to do is make. I have I enjoy working on cars as a hobby. So I was trying to pick my brain for things that aren't related to vehicles. But music, I'd say, was probably a key one of those that's not related to engineering. Although having said that, I'm now going to try and make a guitar. So I sort of I think engineering creeps its way into every one of my hobbies, I'm afraid.
I suppose, however, it still links to engineering, but you I think you feel more creative, don't you, when you're doing something a little bit different from just your job, everyday job. When you're creating, I think it makes you more creative. And I think the young engineers who are listening as well, whatever they do, I think they'll become creative from whatever they do outside of their jobs in the future or anything like that.
Absolutely, yeah.
So Lakindu's asking, how long does it take to make clay models of cars?
Oh, wow. I'm going to be honest, I don't know the answer to that question. It depends on how you go about doing it. In the past, so it also depends on the scale. So very early on, you'll create quite small clay models, maybe a 20th size of a normal car, and you can you can produce those relatively quickly. I'm sorry that I don't know a time scale, but as you start then narrowing down the designs, you start scaling up to the sort of more normal size, so that you can start refining the details on the car. And so the other thing that factors in is the machines that you use. So more recently, people have been using milling machines. A milling machine is a bit like a drill that cuts sideways. So I haven't explained that very well, but essentially what you can do is you can put down a block of clay. You can then give it a computer model of a car, and it will then mill it out of the clay. So it will drill the clay away until it looks very close to the shape that you wanted. And then designers will come and sculpt the clay and refine it. So it all depends on the machinery that you have available and the scale that you're looking to replicate.
So we've got a question from Facebook. So due to the current COVID lockdown, we're seeing kind of less cars on the road, which has had a positive impact on the environment. Has this changed Ford's thinking process of making environmental improvements going forward, you know, Oliver?
That's a very good question. I think the answer is yes, of course, because the question is to what degree. I think if it wasn't to the degree that you might expect, it's probably because you might be unaware of how much the environment affects what companies like Ford already do. This was something that was a shock to me when I joined, but I think most people would be quite surprised at how much of the work that goes into designing a car and an engine is actually for efficiency gains and in order to meet legislation. I wouldn't want to put a number on it, but essentially everything that we do is trying to meet a metric that our customer wants, whether it be acceleration or whether they want it to have a fun spoiler or something. Everything like that is calculated to see what the effect would be on CO2 and the emissions. And if the price in terms of an increase in emissions is too high, then that decision just is made. It's a very easy decision. You just say, "I'm sorry, that would make the car too inefficient, so we can't adopt that." So I think yes, changes are coming, but actually I think those changes have been coming for a long time. So I don't think we'll need a gear change. But I think what's actually happening is that Ford is able to push some of the theories that they've been pushing for a long time, perhaps with more conviction, or slightly more easily than they could do before. But I suppose the short answer is I think Ford's been doing this for a very long time, and I think that actually what's happening is that the things that Ford has put in place over the last decade will now be even more fruitful, given COVID-19 is hopefully opening people's eyes that little bit more to how much we need to do to save the environment.
I think that's kind of a really good theme for children to think about when they are designing an invention for our Leaders Award competition, is something around the environment, and maybe something around cars and around, well, something to do with Ford. They could link it to Ford somehow. I think that's a really good theme to think about. We've got one from Lakindi. I think you touched on this before about because of COVID-19, do you work from home?
Yes, yeah. So I'm currently in my dining room / office. It's actually it's had its benefits. As I say, I've got two cars on the drive that I'm working on at the moment. Normally they're on the other side of the site, and as you might have seen from the map that I showed you, it's a good 15-minute walk from my desk to the car. So one of the things I found is that actually Ford had a lot of the systems in place that we needed to work remotely already in place. That's not to say that there haven't been changes, there have, but actually it's been surprisingly seamless. And for a lot of the work I do, as I said, linking into one of the earlier questions, a lot of the work I do is code related. So I actually spend quite a lot of my time at my desk looking through code and then testing that code in the vehicle. One thing that's been very helpful is that everybody's just a Skype message away. So with the right balance of instant messaging and emails and WebEx meetings and meetings just like this, we've actually been able to run surprisingly efficiently. In fact, my team, the team that I work for, has been commended for being able to carry on almost unaffected by what's happened with us being moved remotely.
We've just got a really nice message from Katie saying this is really interesting, so they're really enjoying it all over.
Oh, good.
She's also said, is a Mustang engine harder to build than a Focus engine?
No. Everything in engineering is about compromise. And so you could produce a Focus engine to be as powerful as a Mustang engine, but it would end up costing too much. It wouldn't be economical enough. And so in terms of difficulty of assembly, all of our engines are designed to very strict requirements. So the engine goes through the factory much like a car goes through the factory, and it stops. It goes through like a roller coaster, but very slowly. It moves to one station to the next, and then you have 30 seconds to assemble an engine. So an operator will stand and he'll have, say 6 bolts. The bit will come down and he'll put in 6 bolts, and then it'll move along. So that process doesn't change depending on the engine that you build. What changes is the compromises that you make. So I was saying earlier that we would have a decision. So somebody would say, okay, I think I can double the power. And then someone else will say, okay, well, what will that do for our efficiency? So you calculate the effect that it has on efficiency. Now, to our Focus customers, that would be too big a sacrifice to make. They don't want to be using that much fuel to get to work and back, for example, or to go to the shops. Now, to a Mustang user who's buying it as a Halo product, as something that they're buying in order to have that power, they're more willing to make that sacrifice to pay for more fuel use in order to get that power. So it's not about difficulty of manufacturing or design. It's about what the compromises are that you make as you design that product.
So we've got a good question from Brian here. So what is your favorite test to do on the cars?
My favorite test. I was doing one recently on our track that was fun, which was a boost test. So I had, what did I have to do? I had to pull the vacuum feed. So the turbo wastegate, which is a little penny that redirects the air either through the turbo or not, is fed by a vacuum. And I had to pull that pipe, and then I had to accelerate as quickly as I could up and down the track to make sure that the computer could detect that the turbo wasn't working properly. But of course, in order to heal it, I then had to put the vacuum pipe back in and then boost up and down with the turbo working 100%. So that was exciting to be accelerating down the track very quickly and very often to try and do this for my job. That's a bit surreal when someone's asking you to step into a Fiesta ST and hoon it as part of your work.
So we've got a question here. So you were talking about the Ford engineer, all the Ford engineer jobs before, Oliver. They said, are all the jobs at Ford kind of engineer job based?
No, absolutely not. I called it the Dunton Technical Centre. I shouldn't have called it that. We recently were renamed the Dunton Campus for that very purpose. We now have loads of Ford Credit people on board. So as you can imagine, a car doesn't just need engineers working on it. Otherwise, we'd never be able to sell it. So we have marketing departments. We have IT departments that not only make sure our systems work as they should do, but we also make sure that they work closely with marketing so that we can have publicity for our products on all the media that we need, whether it be posters or Facebook or TikTok, I imagine even. So there's everything that you can imagine to push a product from childcare. We have a nursery on site to hairdressers, to canteen staff, to cleaning staff, to engineers, to finance, IT. What else have we got? All sorts of stuff. Manufacturing is a different skill set of engineering altogether again. So no, there's basically every job you can think of on site.
So we've got a good one from Lakinda. So what happens if the car falls off the yellow thing that holds the cars?
That's another good question. One of the things, as I was just saying about manufacturing engineering, one of the key things that we do is we design plants in a way so as to minimize downtime. Downtime is very heavily frowned upon in a plant. So, of course, if it's a safety issue, you hit the button, the whole thing stops. But for every 30 seconds that you waste, some customer won't be getting their car on time. Because as you can imagine, we have big ships at these plants that pick these cars up and go. If you're 30 seconds late and that ship's gone, then that customer's going to have to wait for that ship to come back. So you try to minimize your delays as much as possible. If one of those things were to fail, I'd like to think that there were a procedure in place to pick the cart up, move it to one side as quickly as possible so that we can get the line going, and then you would concentrate on the cart and car once it had been removed from the line, so that you were no longer keeping the line stopped. So keeping the line moving in a safe way is the top priority.
So Rohan's asking, what gives the ideas for new cars and their body shape?
That's a good question. I've not personally been involved in the design, but I have been through our design showroom. Goodness, wow. The real answer is that I do not know. When I've looked at the design showroom, you tend to see a lot of mood boards. So what tends to happen is that we tend to try and identify who our customer will be first. So for example, if we were selling a car to a Mustang enthusiast, a key part of that would be heritage. So they would look at what it is that made Mustang what it is now. So they would look at certain sculpture lines. They'd look at what they refer to as shoulders. They'd look at the aggression of the front, for example. And they would look to replicate that in the model cars, which I think is referred to as an homage to the heritage line. So they even do things like make the gear stick slightly harder to move, make the clutch slightly harder to push in to give it that responsive feel. Now, if you're making a Transit Connect van, for example, that's not what they care about. They don't care about the heritage line of the field. What they care about is having a product that does exactly what you want it to do, and does it efficiently and does it reliably. So they will be looking at what the running costs are. They'll be looking at how often one breaks down. They'll be looking at what the repair costs are. They also look at little things, design features, like if you go into a Transit, the knobs are all a bit bigger because you want to be able to manipulate them with gloves on. So that the feedback from the clicks will be slightly louder. The cup holders will be slightly bigger. Things like that. The pedal arrangement will be thought about so that you can control them using big boots. What we don't want is people that use these vans to have to change shoes to drive their van. And we don't want it to be unsafe. We don't want the pedals to be so close together that a big boot might push two pedals at the same time. Whereas in something like a Mustang or say the GT, we would expect that the driver is wearing narrower shoes, normal shoes, if not racing shoes. And you'd be able to have the pedals closer together and with finer precision, so you've got finer control. So I'm afraid I can't tell you much about the exterior design, but I can tell you that a lot of work goes into it. And those are the sorts of cues they try to use.
Yeah, I think that touches on kind of the design process, and I think you mentioned about doing it for the customer. So you need to think about the customer first before you design. And I think that's what the young engineers need to think about. If they're ever doing a design, they need to think about their audience and who they're doing it for, and if it fits, if their design fits that audience as well.
Absolutely. And you might be quite surprised to see the profiles that they create, the detail that they go into. So for the Mustang customer, they would tend to choose an age range. They tend to say, what would their average income be? What would their family be like? What are the general activities that they would do? And then the idea is that you design the product in order to meet that profile that you've created.
I think we've got time just for one more question, if that's okay, Oliver. So we've got one from Katie. So what was the most exciting part of your job, do you think?
The most exciting part of my job? I think what's exciting about my job is the scale of it all. I think I was asked before, what's the difference between you and a mechanic? Or I'd been asked how many cars I'd fixed. And the interesting thing is, there was an example where something had gone wrong. So I had to fly out to Spain to the plant, investigate what the problem was, and then coordinate a fix. And that fix then went in, but it took a week. So suddenly you saw the car park, every 30 seconds the car came out, that car park filled up and those cars couldn't get shipped. To then come up with a fix that went in and has worked successfully for a couple of years. That's what I find exciting, to suddenly know to feel that the changes that you make at your desk and the changes that you make to the code or to the calibration are changes that are having real world effects and being used by customers, millions of customers around the world. That to me is exciting.
Thank you very much, Ola. I'd just like to ask, just right at the end, is there any kind of advice you could give to our young engineers that are listening, or even if you want to think about maybe a design that you would have for the Leaders Award if you were doing it as well?
Oh goodness, I'd say my advice would be to do something that you're passionate about. My siblings, I've seen as we've grown up, we've ended up pursuing careers in fields that we're passionate about, and that's what makes the difference between a spreadsheet just being numbers that you don't want to look at and being numbers that excite you. That would be my advice. Find a field or an area that excites you, and I think the corny phrase is "you'll never have to work a day in your life." And that for me would be the key takeaway message. Find something that you're passionate about and pursue a career in that. In terms of the challenge, is this something that you have to be able to design at home, Alex?
It's just something all the engineers are doing is they're going to just draw a design, so it can be anything in the world, from a worldwide problem to something small like just getting out of bed in the morning. It could be something to help your job.
Okay. Well, I don't have an idea, but I can show you something I've been working on.
Oh yes, perfect.
So to give you an idea, because I've been stuck at home, I've got a car that doesn't have a phone holder in it, and so what I've done, much to my wife's annoyance, I'm sure, is I've pulled the tray out of the car, and then I've gone and designed a little bit in CAD that my brother printed for me, which just slots into here. And the idea is then that I can rest my phone against. So this is sorry, it was just what's lying behind me. But the idea is then that my phone lies in the case like this. So it's a silly example, but it was one of the things I thought, here's something that's bothering me. Here's a problem that is affecting me, and I'm sure other people that want the same thing. How would I go about solving that problem? And that was the solution I came up with. So I'd recommend that would be the project, I suppose, that I've done most recently that's amusing me at the moment. That's the sort of thing that I think I would aim for. Something little, something niggly that's annoying you, and you think actually there's a solution to this, and it wouldn't be that difficult to come up with.
Yes, that's brilliant. That's exactly what the engineers need to think about. Is a small. It could be a small problem, big problem, a small problem, like you said then and showed, and design something around that, which you've already done, which is perfect, which is brilliant, Oliver.
Okay,
I think I'd take that as well, which is fantastic. I just want to say a big thank you to all those who have been watching and sending in their questions. I'm sure Oliver will agree they've been amazing. The questions that have been coming in today, and lots of questions. We haven't been able to go through absolutely all of them because loads have been coming through. So thank you everyone for sending those in. I'd also want to say a big thank you to you, Oliver, for taking time of your day to do this. I hope you enjoyed it as well, as much as we did at the Leaders Award and the attendees did as well. I hope everyone has been inspired to take on the Leaders Award competition and now start designing their own inventions. Make sure to use our resources on our website, www.leadersaward.com, to help you, and please join us for our upcoming interviews. Later today we've also got one at 1:30 with Yulia Motuk, who is a robotics engineer from Leighton Tech UK as well. So as well, I've linked in a survey for you to complete. I'll link that in the chat there if you could do that, and that'll help us relay some feedback to Oliver as well. Thank you to everyone joining us today, and I think we'll end it there. Thank you. Goodbye, everyone.
Thanks. Bye.